talked about carbon-carbon bond forming reactions, and we had gone through basically most of the ones that we had seen before. And one of the things to notice is a lot of these are bonds between sp3 carbons. So in this nucleophilic addition to aldehydes, where you make a secondary alcohol, the new bond you have made is a carbon-carbon bond between sp3 carbons. A related reaction is Grignard with an ester, which makes two new carbon-carbon bonds, but again, both between sp3 carbons. You've got conjugate addition of a cuprate. You've got enolate alkylation, which we've talked about. The aldol reaction makes a new carbon-carbon bond between sp3 carbons, though I suppose if you go on to do the dehydration, you could say, well, you make a bond, both sigma and pi, between sp2 carbons. Claisen is similar. Excuse me. The Michael reaction makes a new carbon-carbon bond between the alpha carbon of the enolate and the beta carbon of the alpha-beta unsaturated carbonyl compound. One that you learned from 351 is this SN2 reaction, and this is unusual because you make a bond between an sp carbon and an sp3 carbon. We have had some experience with sp2 carbons. If you think about reaction of cuprates with acid chlorides to get ketones, the new bond you make is between an sp2 carbon and an sp3. The Wittig reaction was somewhat unusual, in which you basically cut these two bonds apart and then stitch the two sides together. You end up making both sigma and pi bonds between sp2 carbons. Friedel-Crafts alkylation or acylation involved the sp2 aryl carbon and then either an sp3 of the alkyl group or an sp2 of the acyl group. But you remember that with electrophilic aromatic substitution, there's sometimes regioselectivity problems. There's sometimes carbocation rearrangement problems. And so we need alternatives to this. One that I forgot about, but I remembered you guys learned in 351 this year, was Diels-Alder, which makes two new sp3 bonds between sp3 carbons and a six-membered ring, so you can build up complexity. One of the most beautiful things about carbon is all the different shapes it can form. Tetrahedra, trigonal planar, linear. There's a lot of different structures you can build with those building blocks. But so far we're limited in the sense that we don't have a lot of great ways of making bonds between sp2 carbons like this aryl-aryl bond or this bond between an aryl sp2 carbon and a vinyl sp2 carbon. And so in this chapter we're going to learn about some new reactions that can do this chemistry, and three of them that we learn are Nobel Prize winning reactions. And within the past few years, or at least, well, okay, few, I mean in the past 20 years, my scientific lifetime anyway. But they're important because they've enabled access to all kinds of new bonds, and that's really facilitated drug discovery. So I'm going to introduce a few reactions that make these kinds of bonds. And these are going to be called cuprate coupling reactions. And these aren't the most famous or even efficient of the reactions, but they give us an interesting introduction using a reagent that you've encountered before. So in this reaction, we will take an alkyl halide. Let's go ahead and say bromide. And we'll take the diphenyl cuprate. And we will make a new bond between the alkyl group on the alkyl halide and one of the phenyl groups. Okay, and you could be forgiven for thinking this might be SN2-like. I mean, an interesting mechanistic hypothesis would be to think of cuprate, as we've done before, as carrying a negatively charged carbon and then that doing an SN2 reaction. But before you draw that conclusion, let me show you some evidence that it's more complicated than that. You can get the same product from this alkyl halide and this cuprate. And it's a little bit difficult to invoke SN2 as a potential mechanism here, because of course we don't do SN2 at aryl carbons. SN2 requires backside attack, and the backside of that carbon is in the middle of the benzene ring, and a nucleophile simply cannot get there. Nor have we done SN1 where Cl dissociates completely to give us a carbocation. Ever, right? So something more complicated has to be going on, and that's highlighted by this third example in which you can take this vinyl bromide and the diphenyl cuprate, and you can make a bond between the vinyl carbon and the benzene ring. Okay? So if it's not SN2, what is it? And there is an answer to that question, but before we can answer it, we've got to learn a few things about transition metals. So I'm sorry, because for most of this class we have ignored the fact that transition metals exist, and when they've popped up in reagents, we've shrugged our shoulders and say, we don't need to know what the mechanism is. No more, right? And if you have a hard time thinking about transition metals or remembering them, I have this little app on my phone called Atomus, and the goal here is to fuse atoms together, turn 2 hydrogens into a helium, turn 2 heliums. It doesn't make any mathematical sense, and it's not actually even chemically realistic, but it does take you one by one through all the elements, and your goal is to make the biggest one possible. So now I'm used to at least the first row, the transition metals. So it's probably not worth a lot of time or effort, and probably, unless you're a nerd, you won't really like it. So what it's worth. All right. So what we need to do is go through, we need to talk about the number of valence electrons that come with each transition metal. And then we need to learn a new way of thinking about charges and oxidation state in transition metal complexes. And this is going to be unusual to you because we're going to start doing some weird things like not draw formal charge on individual atoms. And this disturbs your classmates in the 9 o'clock class, so I'm going to try to ease you into it a little bit better than I did for them. So let's talk about valence electrons. Scandium, titanium, vanadium, chromium, manganese. I suppose you can go online and learn the little songs about these things if you want to. Let's see. Iron, cobalt, nickel, copper, zinc. And then in the same column as chromium, molybdenum is useful. We're going to see ruthenium later. That's one row down from iron. Osmium is one row down from ruthenium. You have seen osmium before in the osmium tetroxide-based dihydroxylation of alkenes. Rhodium is in the same row of no, it's not Rd, it's Rh. Rhodium is in the same row of the periodic table as cobalt. Iridium is below that, and that sometimes shows up. Palladium below nickel, that's a very, very frequently used transition metal. Platinum sometimes. And there are others that find uses, but those are sort of the ones you will hear about. In terms of valence electrons, it's just column of the periodic table. So 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You'll notice that on the left side of scandium, you've got 2 other atoms. So that's why at scandium we start with 3 valence electrons. We're not going to consider the 4s orbital as being closed. And in fact, many times the electrons that are technically in columns where they come from the 4s orbital, we're going to be involved in the d orbitals of the transition metals. Don't worry, we're not going to talk a lot about orbitals. All right. And notice that by the time you get to the Nobel gas over here, krypton, that row has 18 atoms in it. And so atoms in that row have space in their valence orbitals for 18 electrons. So 18 is the new 8. Instead of the octet rule, we have the 18-tet rule or something like that. I'm sure there's a way to say that fancy, but don't care. All right. So now that we know about the valence electrons available to transition metals, we need to get good at analyzing their complexes, because most of the time the things that do chemistry are not, you don't just throw in general a chunk of iron in the flask and then the reaction happens. You have a reagent that's a complex of other things with the transition metal, and then that does the chemistry. So let's talk about transition metals in complexes. One of the rules with drawing transition metal complexes is you have to show the overall charge on the complex. If it's not shown, it's neutral. So here is a transition metal complex. We're not going to worry very much about geometry of these complexes. If you want to know more about that, you could take inorganic chemistry. This is tetrakis triphenylphosphine palladium. And overall, the complex is neutral. Now, one of the boringest reactions that a complex can do is called ligand dissociation. Okay, and when the phosphine ligand leaves, oops, I did that before too. When the phosphine ligand leaves, it's neutral. Almost as though there's a spot here left behind. I mean, we could draw it or not, but it's a spot left behind where the ligand used to be. Okay, and the ligand will leave as this neutral phosphine. Now, phosphorus is on the same column of the periodic table as nitrogen. That's why we call this a phosphine, analogous to an amine. And the ligand is neutral as it leaves. Now, you may be troubled at this point, because in the past, when we've had 4 bonds to nitrogen, for example here, we would have a positive formal charge on the nitrogen, okay, to keep track of the number of electrons. Of course, we could also have done something like this, and that would have been fine too, but so far with carbon-based molecules, we've used formal charge as sort of a way to guide our understanding of reactivity. Here, we are not showing formal charge on any of the atoms. So I could do this, and this, and this, and this, but then I'd have to, if the complex were neutral, I'd have to put like 4 minus on the palladium, and that communicates that palladium's especially electron rich, and that's not necessarily reflective of reality. So with transition metal complexes, when you have a ligand that dissociates neutral, we call this an L-type ligand. And the electrons that leave with that L-type ligand, we are going to count as though they belong to the ligand. So that's why you don't need, you remember formal charge, right? An atom owns all of its lone pairs and half of its bonds in, half of the electrons in its bonds. So hydronium, water owns 5, right? Here, instead of saying phosphorus owns just one of those two, we're saying phosphorus owns both of them. Okay? So when you see a bond between an L-type ligand and a metal, you need to think those electrons came with the ligand. And then when the ligand dissociates, they left. All right? Questions about that? Go ahead.
How can you predict if it's going to be an L-type ligand?
You draw it. How can you predict if it's an L-type ligand? You draw it with its electrons after it's left, and you see whether it's neutral or not. So let me go ahead. Was there another? Yeah.
And that's only with L-type ligands that the electrons belong to the ligand?
No, with all the ligands, we're going to count the electrons as belonging to the ligand. It's only that L-type ligands are neutral and X-type ligands are negatively charged. So let me show you a different complex. Then we're going to put bromine there, and we're also going to do ligand dissociation. The complex is neutral to begin with. I don't have to write that it's neutral. The absence of a charge shows me that. When we do ligand dissociation, the ligand Br left as Br minus. Therefore, what charge must the remaining complex have? Plus, right? Okay. So there's a difference between L-type ligands and X-type ligands. This is almost the language of Pokemon. Water type versus, I just don't understand, actually. My children grew up playing Pokemon and all of this stuff, and I just don't get it. So if somebody can explain to me at some point, I would appreciate that. Because when Jack, the 16-year-old, is playing Pokemon Go, and I just found a shiny something or other, and I'm like, yeah, okay.
It means he's very lucky.
That's good? Okay, congratulations. It means he's lucky. And I remember hearing names like Mega Rayquaza, and that was supposed to be really awesome or something. I just don't get it. But all right, let me show you some familiar L-type ligands, things that you will encounter and that you need to recognize as being ligands that are neutral. So phosphines, lone pair there. Amino groups, we're going to use R3 here. The R could be either a proton or an alkyl group. Water is an L-type ligand. Also, carbonyl oxygens are frequently L-type ligands. Anytime you've got a lone pair. I'm going to use the yellow color in our discussion today for L-type ligands. Let's see what else. Actually, even pi bonds can be L-type ligands. Pi electrons can donate into the metal. All right. In contrast, X-type ligands are going to be basically exactly what you think. For example, halides. I'm going to show the ligand on its own and then bonded to the metal. Hydroxide counts as well. Let's see, an NR2 minus group. So this is not an amine, this is a deprotonated amine. What else shows up on this list? Basically, any anion you can think of. A thiolate can be an X-type ligand. And then also alkyl or aryl groups. So I'm going to represent that just by R minus, are X-type ligands. And this is important because we're going to use whether or not these ligands have charges as a way to determine the reactivity of the metal. So we'll use pink for X-type ligands. Somebody asked her in the first hour, can you convert an L-type ligand into an X-type ligand? Sure, and in fact, a lot of transition metals will bind water as an L-type ligand. That lowers the pKa of one of those protons. It gets removed and becomes an X-type ligand. So that kind of thing can happen. All right. So with that in mind, what we're going to do now is analyze some transition metal complexes. And our goal for each is we want to determine the number of d electrons, the total number of electrons in the complex, and we want to determine the oxidation state of the metal. Okay? So let me begin with cobalt, with a cobalt complex. And again, these are L-type ligands. So when you see this, you must think of those bonds as being lone pairs that are owned entirely by the ligand and not by the metal. And I think this is what troubled your classmates during the 9 o'clock hour, because they saw this and thought, why are there not pluses on those nitrogens? And the answer is because if we did put pluses on all of those nitrogens, in order to balance the overall charge, we would have to put a 3- on the metal. But actually, we're going to see the metal's at the +3 oxidation state. So putting a 3- on the metal is physically unreasonable, even though it would be an okay way of counting electrons. So we're going to work on the understanding that the electrons in the bonds between metal and ligand belong to and are owned by the ligand. Right? So we're not going to put formal charges there. Okay? Now, let's deal with first the total number of d electrons on cobalt. You know that we have 6 L-type ligands, and they are all neutral. So if we dissociated all of them, what would be the charge on cobalt? +3, right? Because the ligands are neutral, so the only thing that can be the charge is the one on cobalt. So cobalt is in the +3 oxidation state. We can draw that like this. Okay. Now, how many d electrons? I am really sorry, folks. My zipper is ding-a-ling-a-linging against... Okay, here, hold on just a second. Won't you be my neighbor? Is that driving you crazy? What the heck is that? That was a dumb idea. Wonder what we're going to do now. Is that better? Sorry. All right, how many d electrons? Well, first, to determine that, we're going to take the number of valence electrons minus the oxidation state of the metal. So, cobalt comes with 9 valence electrons. It has a +3 charge, so it must have 6 d electrons. So people will call this a D6 complex. Do you see how we did that? Go ahead.
How did you know that cobalt was a 3+ charge?
How did I know cobalt was a 3+ charge? I was given the information that the complex had a 3+ charge. Then I looked at all the ligands and they were all L-type, which means none of them have a negative charge or a positive charge. So all of that plus has to be on the metal. Yeah. Go ahead.
And why is one of them an NH2?
Because I'm an idiot. That's true. Sorry, that was just my mistake. Thank you. What else? Okay. All right. Other questions about that process? So your text does not take you through this. Go ahead.
maybe a dumb question, but what do you mean by d electrons?
D electrons, that means how many electrons are in the d orbitals on cobalt. So cobalt or these transition metals have 5 d orbitals, and we're going to count the electrons that remain after we subtracted the oxidation state as all belonging to those d orbitals. Because even though you've been taught you fill the 4s orbital first, when the metal is bound by ligands, the 4s orbital is still close to the nucleus. It's the d orbitals that are out there, and their energy is lowered by those ligands. And so we're going to fill the d orbitals first in complexes. Yeah. Okay, what else? So let's count, now that we know the number of d electrons, let's see what the overall electron count is, right? We have 6 from cobalt 3, and then we have 2 times 6 from ligands for a total of 18 electrons. That is a noble gas configuration. That is, we filled all the valence orbitals there. This is the new octet rule for transition metal complexes, maximum of 18 electrons. Because each s orbital, the s orbital can take 2, the 5 d orbitals can take 10, the 3 p orbitals can take 6, and that gets you to 18. So that's our new deca-octet rule instead of regular octet. Okay? So as I was saying, your text doesn't take you through this process. It's important, though, because it's going to help you understand the mechanistic steps that we deal with these metals. And I will give you some more examples to work on a little bit later. Let's do a couple more. So let's now do one of those cuprate complexes. We can be specific here. You know, I could have gaslit all of you and said, what ringing sound? There's no ringing sound, right? Gaslighting is bad, don't do it. So the overall charge on this complex is, and we'll just forget about the lithium, which is a counterion, is negative. Now, both of these ligands are what type? If they left, they are X type. If they left with their electrons, they would be negatively charged, right? We've got 2 of them. Okay, so we've got 2 X-type ligands. Now, the overall charge on the complex is negative. If we have 2 X-type ligands, what charge should be on the copper to get to this right number? +1, right? So so if the complex charge is -1, copper has to be +1. And we can write that in a couple of different ways. Now let's figure out how many d electrons. We've got, for copper, 11 valence electrons, and then -1 for oxidation state. So that means there are 10 d electrons. Or this is a D10 complex. And then overall number of electrons, let's add the 2 times 2 electrons for the 2 R-type ligands, and then the 10 d electrons. Overall, 14 electrons. Okay, so we got 14 d electrons, so you might not be surprised. There's space for more. You might not be surprised if copper could accommodate 1 or 2 more L-type ligands. And I don't know the extent to which that happens. Okay. Let's do this one. Drawing a neutral complex. All right, so overall this complex is neutral. These ligands here are interesting because they are L-type here, but X-type there. These are acetate anions. They would leave as this. So the carbonyl oxygen is an L site, that's a neutral ligand, and the negatively charged oxygen is an X-type ligand. So if the complex is neutral overall, what is the oxidation state of palladium? It has to be +2, right? And we will write that as palladium 2, just to balance out the charge. Okay? Let's figure out the number of d electrons. Palladium comes with 9 valence electrons. Nope, that's wrong, 10. Palladium comes with 10 valence electrons. We're going to minus 2 for the oxidation state, and that is 8 d electrons, or this is a D8 complex. 8 electrons available in the d orbitals to palladium. And then overall number of electrons in the complex, you've got 8 d electrons. Then you have, from each of these ligands, 2, 4, 6, 8. So 8 electrons from ligands, and that leads to a overall 16 electron complex. Okay. Question so far? Go ahead.
On the copper one, why was it 10 valence electrons?
Copper has 11 valence electrons, but it's in the +1 oxidation state, so we're missing one, so that's why we have 10 d electrons. Yep. I'm getting cold now, but I think now that it's the mic is attached to my shirt, maybe the ding-a-ling-a-ling-a-ling-a-ling zipper. This is going really well. Zipper. 42 years old and still struggling to put on a jacket. Speaking of being old and struggling with clothing, so I happen to own a Darth Vader costume. If you visited my office, the helmet is sitting on my microwave. I don't know why. But periodically I bring it, and sometimes around Halloween, Dr. Michaelis and I have a lightsaber battle. And so on one of those days, I had brought in the costume, was trying to get dressed in my office, but it zips up the back, and I'm not very flexible, right? And so I had this brilliant idea. I'm going to take a shoelace and loop it through the zipper. I'm going to get up on my tiptoes and throw that loop over a coat hook, and then I'm gradually going to lean down and let that thing zip me up. And it went well at first, but then the zipper snapped, and I was really sad. And but fortunately, so I was telling my family about it, and my mom was like, "Well, just bring it over. I'll fix it." And I thought, I'm a 40-year-old man whose mommy is still fixing his Darth Vader costume. So I let it be that way for a while, and then I actually bought the zipper myself, and I pinned it in carefully, and then Amber sewed the zipper on. So at least it wasn't my mom, right? Okay, well, other questions about oxidation state? Yeah.
So the 8 electrons come from each of the bonds connected to the ligand, is that correct?
That's right. The 8 electrons here from the ligands are from each of these bonds, and each of these electrons belong to the oxygen atoms. Okay? So it's not actually that hard once you remember that the bonds belong to the ligands, not the metal. All right? One last one with palladium. This is kind of interesting. Sorry. Okay, this one's going to drive you crazy. Because when you see this, you have to imagine, you have to realize and know that this alkene is an L-type ligand, and that this bond represents the pi electrons donating to the metal. So actually, probably better would be to do something like this, but sometimes people won't. They'll just do this. And so you have to sort of know the lingo. You have to know the secrets, right? This extra bond, this bond here doesn't mean an extra pair of electrons. It means the pi electrons interacting with the metal. Okay? Maybe to make things easier. Well, no, we're just gonna suck it up and deal with the way people draw things. All right, it's bromine here. So you've got an L-type ligand there, an L-type ligand there, an X-type ligand there, and an X-type ligand there. The overall complex is neutral. So if we've got two X-type ligands and the complex is neutral, what is the oxidation state of palladium? +2, right? Or palladium 2. Number of d electrons on palladium. Palladium comes with 10 valence electrons, but we've lost 2 from the oxidation state. So we have overall D8 complex, 8 d electrons. And our overall electron count is, so from X-type ligand, from L-type ligands, 2, 4, and then 6. And then from the X-type ligands, 8 and 10. So we have 8 d electrons, 10 electrons from ligands. So that's overall an 18 electron complex, which would have noble gas configuration. It's got a complete set of electrons. All right, so this is how you think about transition metal complexes. And honestly, I used to sit and listen to people talk about this in like seminars in grad school, and I had no idea what they were talking about, and it was frustrating. And I'm kind of glad that after all these years, Dr. Michaelis is now teaching all of us how to do this. Okay. So who cares about all this stuff? Let's look at a mechanism of a reaction, and you're going to see that counting the electrons on the metal is going to help you see what is going on. So let's look at one of those cuprate coupling reactions that we dealt with. I don't know which one we want to do. Let's do this one. Okay. We've said before, based on our analysis above, that copper here is in the +1 oxidation state, and that it has, let's see, copper comes with, see, I can't do this in my head yet. It's got 10 d electrons. All right, so we're going to forget about the counter ion for now. And I'm going to put the negative charge just on the complex overall. And we're going to note that these are two X-type ligands. Now, I told you before, we generally don't draw lone pairs on the metal. But we can draw them when we need them to do chemistry. So what happens here is that we're going to take a pair of electrons from the metal, and we're going to make a new metal carbon bond, and at the same time we're going to have chloro leave and make a new metal chloro bond. The mechanism here is not SN2, it's almost a insertion of the metal into this bond between carbon and chlorine. The arrows are just to keep track of the electrons. Literally, if you were to see this in a movie, what a great movie, right? If you were to see this in a movie, you would literally see this getting closer to the metal, and then these two getting farther apart from each other, the R group and the ligand and the chloro, and both of them close to the metal. So, and so a lot of times people do not even push arrows for this step, but I know as organic chemists we like to. So we make a new copper chlorine bond, and we take 2 electrons and make a copper carbon bond. But as soon as we do that, the new complex that we get is different than it used to be, because we now count, of course, the electrons in the carbon and the copper chloro bond belong to chloro because it is an X-type ligand. But now the electrons in the bond between the phenyl group and copper, what a horrible bond that is, goodness. All right, let's try this. The electrons in the bond between the phenyl group and the copper, which came from the copper, actually now belong to the carbon. So it's like copper has been oxidized and carbon has been reduced. Carbon has stolen 2 electrons from copper. Now, the overall charge on the complex, we added a neutral molecule to this complex, so the overall charge has to be the same. It's still -1, but now we have 4 X-type ligands on copper, and if we want to end up with only -1, copper has to be at what oxidation state? -1, -1, -1, -1. 4 minus plus 3 equals 1 minus. So it's copper 3. And if we count the number of d electrons that copper has, 11 valence electrons minus 3 oxidation state equals D8. So copper loses 2 electrons, and we call this reaction oxidative addition. Let's see, let's deal with the overall electron count. Copper is D10 here, and then you have 2 electrons from that ligand, 2 from that ligand, so overall 14 electron complex. Here in this copper 3 complex, we have 2, 4, 6, 8 electrons from ligands. So overall, we have 16 electrons in this complex. So this may be one reason why, I mean, I'm hand waving now, but one reason why this can happen is because you get the complex closer to its noble gas configuration. All right, so that's oxidative addition, where we are inserting the metal in between a carbon halide bond. In so doing, we take 2 electrons that were from the metal and we give them to carbon. Okay, now the cool thing is that in the next step, we're going to have the electrons from one of these X ligands form a new carbon-carbon bond with the benzene carbon. And now these electrons between copper and the benzene carbon are going to go back on the copper with a sigh of relief. It used to be oxidized, now it's not. So the new bond that we make is right here between the benzene ring and the alkyl group, 1, 2, 3, 4 atoms. What's left behind is this complex And if we count electrons in the same way, you would see that this is a copper 1 complex with D10 electrons and overall 14 electrons in the complex. Okay? This process where electrons from an X ligand go on to the metal is called reductive elimination. And this is not the fancy way, this is not the fancy use of the word reductive as in that's so reductive, right? That you say while swilling your drink at whatever party. You're not the kind of people to do that though, right? That's good. But it's reducing. The electrons go from the bond with the X ligand back onto the metal. I'm going to draw them there, but we don't usually draw those lone pairs. So we go from D10 to D8 back to D10. Yeah?
And why do they go back onto the metal?
Why do the electrons go back onto the metal? Well, they have to go somewhere. We only need 2 of them to make a bond between carbons. Yeah. And actually, it's not at all clear whether I should draw the arrows this way or whether I should draw the arrows this way. I don't think they know, and I don't think it matters. I don't think you can tell. Either way is fine. And in fact, when people are drawing these types of mechanisms, very often they do not use arrows. They just assume you know what's going on. Which, for me, as I was listening to these talks, was not the best assumption. I didn't really know what was going on. Okay. So now we're prepared to talk about a number of interesting new reactions. You've seen oxidative addition and reductive elimination. Let me give you another quick example of that. So we're going to start with a palladium complex. It's going to be palladium tetrakis triphenylphosphine. And then actually we're going to do what's called a ligand dissociation reaction where we're just going to lose 2 triphenylphosphines. The metal stays the same. We just don't have as many ligands present. Ligand dissociation is usually fast and reversible. So this is some equilibrium. If you were to analyze the oxidation state, you would conclude that this is palladium 0. And palladium has, in the 0 oxidation state, has 10 electrons, and overall there would be 18 electrons in the complex. All right, over here we're still palladium 0, it's still D10, but now we only have 14 electrons in the complex. There's space for something else to be a part of. So now we're going to take an aryl iodide. This is a phenyl bond between a benzene ring and an iodide. And we'll do oxidative addition. We're going to have electrons from palladium make a new bond with the benzene carbon, and then electrons from the carbon iodide bond make a new bond with palladium. We will call that oxidative addition. The new complex is still neutral, only we've gone to palladium 2 because we have 2 X-type ligands there. So this has to be palladium 2, D8 electrons. Palladium has 8, and then there are 16 from the, or 8 from the ligands, so that's a 16 electron complex. Okay, so that's just one other oxidative addition step. And we'll continue on. What I'm showing you really is the first few steps of what you'll learn is the Suzuki reaction. Anyway, we'll see you next time. Have a good Monday.